Hello everyone and welcome to the webinar. This is Arun Sharma from MIDAS and I'll be conducting the webinar today for segmental bridge construction, and today we'll be talking about balanced cantilever bridge construction. So this is what we'll be covering today. Kindly bear with me, there is a lag between my transmission and your reception, so I'll try to match the two. So this is what we'll be covering today. First we'll be creating the geometry from scratch, and for this we'll use our free cantilever method or balanced cantilever method bridge wizard, which will allow us to create the geometry, construction stages, assign sections and tendon profiles along with loading to the structure. Then we'll apply time dependent material properties to our bridge and then assign the superimposed dead loads to the structure. Today we'll be just focusing on construction stage analysis in MIDAS and thereby moving on to the results. This is an overview of the bridge geometry. We'll be modeling a 3-span balanced cantilever bridge, and these are the box section. It is a single cell box section, and it is tapered from the pier table location to the center of the bridge. So the dimension of the pier cap or the pier table is given here, and the dimension at the key or the closer section is given this. This will be the construction sequence. We'll start the construction from the pier table, and you can see form traveler mounted on top of the pier table, and the construction as per balanced cantilever bridge approach is carried on both sides of the pier table, and therefore it's called a balanced cantilever bridge construction methodology. Most of the time what happens is we start construction on one of the pier table first. When we are halfway through the span, we start the construction from the other end. So there often exists a lag between the two pier tables. MIDAS Civil is capable of considering such kind of real field scenarios, of considering these time gaps between the construction of different segments. And also one more thing that you can note here is the form traveler. When the form traveler is erected at a particular location, then that means that it is pouring the concrete for the subsequent segment, and then when the concrete sets, it is post tension, and then the form traveler moves to the next location. So there is a sort of moving load applied to the structure that moves from one node to another node at different construction stages, and our wizards will take care of this kind of modeling automatically. Then there is an approach deck or fully shored segment which is very close to the approach deck, and we have this sort of span which we create using some kind of supports underneath it, which is cured for a longer duration, and once it is in position we apply the key segments. So same methodology is applied at the two extreme ends. And this is how a construction schedule usually looks like. You can see on the y-axis there are numbers. Each segment represents, or each line or division represents 15-day timeline here. So you can see that the pier table has 1, 2, 3, 4. It means it is 60 days the total construction time for the pier table, or the curing time. Then for each segment we have given, if you look a little closely, it is 12-day per segment that we give. I beg your pardon, each division is for 12 days. So each segment is given 12 days, and in this 12 days we are giving 7 days for putting up the formwork for each segment, and 5 days is given for curing of that segment. Also, with this timeline you can see that pier table 1 is erected before pier table 2, and there exists a gap of 60 days right here. So you can see they're starting at different time intervals, but the key segment is placed after certain duration when the pier table 2 construction has been, or the segments related to pier table 2 have been completely erected. So I'll show you how the program takes care of such kind of scenarios. Also, this is the fully shored segmental part of the bridge, which is again cured for 60 days and then erected, and then the key segment is poured, which is cured for 10 days. This is the tendon layout that you can see here. You can see in different segments, different number of tendons are anchored. I'll come to these details later on, but for now you can just see that the tendons are started from the these are basically the top tendons which have started from the pier table and then moved onto the cantilever portion in the same format, and then we have the bottom tendons and the continuity tendons that come into picture once the closer sections are erected. So they are as you can see, they have different starting points and different ending points. We can control all these things in our wizards, and automatically such layouts are easily generated. And once the bridge is constructed after the wizard, you can see the complete bridge formation as shown here. So from this point onwards, I'll move on with the real modeling of the bridge. So let me go back into the program and start with a new file. I'll click on model, but before that, as a thumb rule in MIDAS Civil, you should always click on Works tab, because it will show you the progress that you have made so far in your model. So you go to Model, then you go to Structure Wizard, and then select FCM Bridge. FCM stands for free cantilever or fixed cantilever method, but it is more commonly or popularly known as balanced cantilever bridge. So that's why I don't get confused by the name FCM. It is the same thing. Now on this wizard we have 3 tabs. The first tab is model, second is section, third is tendon. So on the model tab we define the overall geometry of the structure. Now this tab in itself is very crucial, and various layouts can be possible using this tab efficiently. You can start by defining the material properties for girders and the pier section you can define here. You can specify what are the number of segments in the fully shored method or the segment of the bridge, what is the dimension for the closer or the key sections, how many segments are there, what are their lengths in zone 1 and zone 2. If the bridge is symmetric, then zone 1 always forms the outermost segments of the last span, and zone 2 are all the interior segments. But if it's asymmetric, you can have zone 1 and zone 2 defined separately as left and right side of the pier table. I'll come to these details a little later, but before that, allow me to start with the material property definition. So to start with materials, I'll just click on this button with 3 dots. It will prompt this dialog box where I can click add to define the material property, or if you have a given set of material property that you want to use, you can just click on import button and import it from the previous project that you have with you. So I'll bring in the material properties for C6000 grade concrete and the steel material for tendons, and then I'll click OK. Upon hitting OK, you can see that under Works tab the material properties are updated, as well as in the properties dialog box. Then I'll move to the section tab. I can either click add and define my sections here, or I can just click on import button and import it from the previous project, what all sections I need. So I just need the peer sections as of now. So I'll select all the other sections and take out from the selected list and then click OK. So now you can see there's just one peer section that we need. You can double click on it and see the properties. It is 70 by 320 rectangular section, and then click close. So we have defined the material for girder and pier. We are using same grade of concrete. You can use different as well. Then we have defined the pier section. The stage duration, as I mentioned, for each segment we'll give 12 days, 7 days of putting of formwork, 5 days of curing. That makes it 12. Number of piers will be 2 since it's a 3-span bridge. It's a cast in place construction. If you want to do a precast sections, you can use the other method as given here, PSM. For today we'll focus on cast in place. Then if the bridge has some kind of curve, you can just click on the radius, select its convex or concave and enter the radius, and the program will generate a curved bridge for you. For the time being we are sticking with the straight bridge. Then you can enter the pier table dimensions. And once you have entered the pier table dimensions, and all these abbreviations that are given here can be read easily from this bitmap image. What they mean, where are they located, what is the significance, you can easily relate with this image and then go back to your drawings, see these parameters and easily enter them here. Let's say you don't want to have same type of pier table, or if you want to have different type of pier table at different piers, so you can just click on advanced and then define different type of pier tables for different locations. Since we have 2 piers here, it is automatically defining PT1, PT2, pier table 1, pier table 2. But if there are 4 or more, it will create that many number of pier tables, and then you can define whether it's a single diaphragm, it's a double diaphragm, and all those variations are possible here. But right now we'll just stick with the given values. Then click on pier table placing, and then you can specify when when is the second pier table erected, or what's the lag between these two placing of these two tables. So as I mentioned in the very beginning, it is 60-day time lag. And then I'll click define, so you will see PT1 and PT2, there's a time difference of 60 days. Then come to K1, that is a key segment. As you can see, K1 forms the exterior most closure section, and K2 forms all the interior closure sections. So you can enter the dimensions or the length for this closure section, which is 78.75 inches here. And then again, as I mentioned, if you don't want to use same length and you want to have different lengths at different locations, you can click on advanced and then modify the same here. Then come to the pier. The height, as you can see, H represents the bottom of the pier table to the support location for the pier. So that will be the complete H, which is 1575. And see if you want to have a twin pier system, that is twin columns under one pier table, you can enter some value for C, otherwise you can leave this value as 0. Today we will be having a twin pier system or twin column pier system, so I'll enter the value of C here. Now you need to enter the fully shored segmental portion. So L means on the left side, R means on the right side. So if they are asymmetric, let's say this have more number of segments on the left side and the right side has less number of segments, so you can modify these right here. But for this case, it will be one section of 78.75. Then we'll have 4 sections or 4 elements of 167.5 inches, and it's a symmetric bridge, so I'll just copy them and paste it in FSM for right side as well. Now coming to zone 1 and zone 2. Zone 1 will define how many elements are there and what is their length. For our case, it is this value is 12 segments of 187 inch each, and since it's symmetric, I'll just copy and paste it right here. Now if you don't want to obey or want to have different number of segments or asymmetric bridge, then you can go to advanced, and then since it's 2 pair right now, you will have this 2 pair, but otherwise you will have all the number of pairs that are there in your bridge, and then you can define different zone 1 and zone 2 on either side of the pair. Now coming to member age, this is very important because this determines how many days you have given for the concrete to acquire the strength, or how many days you have done the curing of this cast in place concrete. So for FSM we'll give 60 days, for the key segments we'll give 10 days, for pier table 15 days, for segments 5 days, because 12 days is for the entire construction stage for each segment, and 5 days is given for curing of concrete, so 7 days is for the form work. So you can interpret from here that how we control the age of the segments. And then the pier age is 100 days. This means that when the loading will first come onto these segments, the concrete has acquired this much maturity, and where this maturity is used for analysis, I'll point it out little later when we define time dependent material properties. Then click OK, and so this completes our first tab. Now moving on to the second tab, where we need to define the section. You can choose from single section or single cell or 2 cell sections, or if you want to have some user defined section, you can go to type 2 and then bring in any section you want for the center and the pier table, and the program will create the balanced cantilever bridge using those sections. But for the time being, I'll stick to a very simple single cell box section and just go ahead and enter the values. Now again, these values can be easily read from this bitmap image right here, and you can see the values are for the key section as well as for the pier table. So I'll just enter the values in there. Six 6.22, 10.25, 13.78, and these values can be very easily read from your drawings. So if you have any cross-section drawing with you, you can directly break them down into these components and then enter these values directly. If you're using type 2, then you can even bring in your sections from the CAD drawings and then create in section property calculator, and then create the section from it and then bring it here. And I would recommend to use that kind of that approach only if your segments are really of or are basically not the common sections. There's some unique shape involved there. Otherwise this is a lot easier approach. So once you have entered these parameters, you can just click on drawing, and then it will show you the 2 sections that are created. One is the closer section, this is the pier table section, and you can also consider the weight of form traveler as well as weight of wet concrete. So if you check this on, you can the program will automatically calculate the section dimension and use the weight of wet concrete and apply them onto the structure before the section is actually erected. The weight of form traveler you can enter as 176.4, and the eccentricity will be 98.5 inches. So this is where you define all the sections. Then we move on to the third and final tab, which is tendon. It is a very interesting tab because you can and it is very intelligently laid down. If you look at this bitmap image right here, you can identify some layers of tendons, and these are the layers of tendon for top tendons in the peer table, and these big circles are the anchorage locations, and this big circle is the third anchorage location for the bottom tendons. So all you need to do is specify what is the level of or the depth or how much, at what depth are these layers uh, are applied in the cross section of the peer table, and you need to specify what is the spacing between the tendons, and basically just give the outer coordinates of these layers, and then specify the number of tendons that will be there, and then specify where the tendons will be anchored in different segments, and the program will automatically use these three information, that is the layout, the tendon number of tendons, and the spacing, and where they are anchored. The program will automatically create the entire uh, tendon profiles for you. It might sound a little complicated right now, but trust me, when I'll show it, it will become very simple. So I'll just start entering the coordinates for the top tendons. And this particular step requires a little bit of uh, thinking and work that you have to do in order to break down the entire profile that you have um, from some DXF format or some other Excel input. But once that is done, that will certainly be very helpful for your generating model using the wizard that includes all the construction stage analysis. But this does not mean that you are bound to use this approach to create the tendon profile. You can create the entire bridge by just checking off tendon and pre-stress. So it will just create the entire construction sequence without the tendon profiles in there. And then you can go and create the tendon profiles manually from your spreadsheet inputs or from your text inputs, and then modify the construction stages accordingly. And there exist several tricks. Sometimes the engineers just enter some value here to generate the bridge, and then just go into the tendon that are created and then replace their values with the exact coordinates that they need. So there are various ways of working around with these features and optimally saving your time and modeling the structure. So once these outer coordinates and the anchorage locations are defined, I'll click on tendon number and then specify how many tendons are there in which group. So N1 is 7, N2 will be 3, and 3 will be 6, and 4 will be 3, and 5 will be 2, and 6 will be 7, and 7 will be 2, and 8 will be 5. So I'll stick with these number of tendons in each group here, and now I'll define the anchorage points in different segments. So for top tendons, let me bring this spreadsheet, this presentation here. If you notice here, we have two tendons being anchored in the peer table. Then from segment 6 to 10, we have two tendons being anchored, and for the similarly for the bottom tendons, we have two tendons anchored in segment I think it's 5, and two tendons being anchored in segment 11. So you can have these kinds of information pretty handy with you, and then while you are defining this, you can just say that okay, for top tendon peer table, I want 2 tendons to be anchored. Then all the others will have 1 1 1 from 6 to 10. I want 2 tendons to be anchored and just defined, so they are modified here, and others remaining 1, and then click OK. Then bottom side tendon, I mean that is the outermost spans. From segment 1 to 4 we don't have any tendon anchored, so we'll have 0. Fifth will have 2 tendons, and 11th will have 2 tendons, and the 12th will have none. So this way you can define the anchorage for the mid and side. Oh, I beg your pardon, I mixed the mid and the side, so let me just quickly fix it. For the side it will be, fifth one will have just 1, and 11th one will also have 1, and 1. Yeah, sorry, I mixed up the side and the mid one. So click OK, because if as I remember, in sides all are just 1, so there are no 2 tendons being anchored in different segments. Whereas in mid we'll be having first 4 to have no anchors, then 5th to have 2, 11th to have 2, and 12th to have none. Click OK. So these 3 things will define the tendon profile for you. You can select whether you want to grout the top tendon at the very pre-stitching step, or you want to grout them in the following construction stage. So like we do in the field, we we tension the tendons, and then while this next segment is being erected, the grouting team does the grouting. So you can control that kind of behavior here. Sometimes we do post tensioning of 3-4 segments together and then grout them in one shot, so the pre-stitching step can be different and the grouting can be like 2 or 3 steps later. And you can also specify where exactly your anchorage block is located. This is the variation in the cross section, and this is the variation in the length of the segment. So if you say 0, this means it is at the very beginning of the segment, and 1 is at the end of the segment. So you can choose any fraction from 0 to 1 where you want to define your anchorage block. If you are dealing with web tendons, you can just check on web tendons and enter those web tendons also. But for balanced cantilever bridge, we will not be using it for now. And then we'll define the tendon property. So you click on this button, you click add, you enter the name as tendon. In MIDAS you can handle all kinds of tensioning. It can be pre-tension, post-tension, or external tendons. So we are dealing with post-tension here. You can select the material for tendons. You can enter the total tendon area. So just by clicking on that button with 3 dots, and then you can select the strand diameter, let's say 0.6 inches, and entering the number of strands, let's say 19, and then clicking OK, the program will automatically calculate the nominal tendon area and enter it here. Then you can enter the duct diameter for each tendon, and then the relaxation coefficient. If you want to compute the relaxation losses, you can choose to do it as per CEBFIP, and you can enter the coefficient as 5 or 2.5% depending upon the type of tendon that you are using. Then you can enter the ultimate strength of the tendon and the yield strength of the tendon. And the curvature friction factor, since it is post tension, so we'll have all these losses: curvature friction factor, wobble friction factor. You can enter these values precisely, and then the anchorage slips, which will be 0.235, sorry, 0.235. So 0.235, and then you can select whether you want to have bonded tendons or unbonded tendons. So we'll select bonded tendons for the time being and then click OK. So this defines the tendon property. Moment we do that, you can see it under the tree menu. So, and you are allowed to use any kind of different tendon properties for top and bottom tendons. Right now we are using just one property. And then you have the jacking stresses. So for the top tendon we want to have 0.72 times of the ultimate stress, and for the bottom also we will have 0.72 times of the ultimate stress. You can choose to have from the yield stress also if you want, and these stresses you have already I mean the strength you have already mentioned in the tendon property. So it is ultimate strength or the yield strength based on which you want to have the multiplier for jacking and applying it as jacking stress. Now once you have done all this, you can always go ahead and save this file with some name. Let's say balance cantilever bridge, and then just click save. So, and next time you want to manipulate something in this wizard, you can just click open and then click on balance cantilever bridge.wzd, which is the wizard file, and all things will be restored as it is. And then you can go ahead and click OK, and the program will generate the entire bridge for you. As you can see here, the bridge is created in front of you. It has all the supports defined, it has all the loading defined, it has all the tendon properties defined, and the construction stages defined. And what I'll do is just display the tendon profile points and the nodal loads onto the structure, and we'll cycle through the construction sequence. Right now we are looking at the base construction stage. So we'll change the construction stage to from base to CS1, which is first construction stage, and I will press down my wheel mouse button and just drag my mouse so you can pan the structure anywhere in the cross section very easily. And then I'll zoom in so that you can see, just by scrolling forward you can zoom in. Now if you look closely into the screen, you will see that there are two tendons per web anchored in the pier table, and then you can see this vertical arrow, which is the point load for the form traveler, and then there is a moment arrow that represents the moment arm or moment that is coming to the pouring of wet concrete for the next segment. So this is your first construction stage. Let me zoom fit, and let me zoom out a bit and fix this view. Now I'll switch to the second construction stage, and here you will see that a new segment, the next segment is erected, and the new pair of tendons are anchored, and the form traveler moves from this location to the next location. Third construction stage, the form traveler jumps to the next location, new segment comes into picture, new set of tendons anchored. Fifth stage, sixth stage, and so on and so forth. And same thing is being done if I zoom fit to the other approaching segment. Right now it appears that they are constructed simultaneously, but there exists a time load that the program is applying internally, and later on you will see the time load that goes to increase the age of the segments associated with one of the pier caps by that much duration. So that effects are automatically taken into account. So now I will switch to the front view or the elevation and cycle through the constructions stages. So in 14th stage, when you see the approach deck or the fully short segmental span is erected, the continuity tendons are placed on the side, I mean on the outermost spans. So basically here it shows that if I zoom in here, this is the bottom mid or bottom side tendons. At the top you have top tendons, and at the bottom you have bottom side and bottom mid. Bottom mid will come in the middle span or the interior spans. So let me just zoom in at this location and move to the final construction stage, where you will see this final segment or the key segment is applied and the continuity tendons come into picture. So the complete engineering concept of such construction methodologies have been built into this software, so you can completely rely on the models that are generated through these wizards and then tweak them a bit based on your requirements and then use it. So I'll show you how we can manipulate these models easily. Let me clear the view by clicking on initial view. Nice view. So what I'll do is first define the time dependent material properties. So right click, go into properties, and then click on time dependent material, creep and shrinkage, and then click add, and then add the name as C6000. So basically you can give any name you want. I chose this name so that I can identify or associate it with the material I'm using. You can select from different codes for creep and shrinkage. As you can see, we have CBFIP 1990, 1978, ACIP, CA combined, ASHTO, and a user defined feature. So even if you are using some set of material properties of your own, you can definitely go ahead and define those curves also in the software. And the reason we choose CBFIP 1990, it is that it gives the best behavior or best concrete behavior against time, and the results are really accurate as compared to other codes that are out there. So but anyways, we have other options. If the contractor wants you to use a particular code, then you have to use it. Otherwise you are good if you are using CBFIP 1990. Anyways, now we'll enter the characteristic strength of the concrete as 6 ksi, relative humidity is 70, the notational size of the member, which is the volume to surface area ratio. Right now we'll just choose it as 12. Now I'll come to this point. It is an arbitrary value for the timing, and later on we'll modify it, because as the section sizes change, these values need to be updated. So program will automatically take care of this, and I'll cover that in a short while. Then what kind of concrete you are using or cement is normal or rapid hardening, and the age of concrete at the beginning of shrinkage is 3 days. Then you click on show result and you will be able to see creep coefficient and shrinkage strain graphs. Now when we say the age of concrete is, let's say 30 days, the program will read when the segment is activated, the age of the concrete is 30 days, and from here onwards it will compute, it will multiply the creep coefficient and the shrinkage strain the segments and go on adding the construction stage duration to the structure. So in this manner the age of concrete plays a crucial role, because that defines the starting point on this curve from which it affects the material properties and the stresses in the sections. I'll click close here and click OK, and then click close. If you are using different type of materials, not just one, you can define several different time dependent material properties for creep and shrinkage. And similarly, if you go to properties, you can define time dependent material compressive strength gain curves. Then you click add here, enter the name, again C6000 I'll use. It can be either code dependent or it can be a user defined. So if you have your own set of parameters, you can just copy paste from the spreadsheets to generate these curves. But for code defined, again you can use ACI, CBFIP and others. I'll stick to CBFIP, and here you need to enter mean compressive strength. This is something peculiar to CBFIP. It is not the characteristic compressive strength, it is the mean compressive strength, which is characteristic compressive strength of the concrete plus standard deviation, which is delta F. So I'll enter 6, which is the characteristic compressive strength of the concrete, plus 1.16, which is the standard deviation or the delta F usually for the concrete. Then you can select what type of cement it is and then click on redraw graph to generate this graph, and then click OK and click close. And age of concrete plays the same role for compressive strength as I mentioned for the creep and shrinkage, based on the day's duration. when you are activating with what age, the program will read the value from there and then carry on. So age of the segments do play significant role. Now we have defined these two material properties, and now time dependent material properties, we'll associate them with the actual material that we are using. So I'll go for time dependent link and then select the creep and shrinkage and the compressor strength gain curve that I just defined and associate with the grade C6000 concrete that I'm using, and then click add or modify. Then I'll scroll down and click close. So basically in this manner you can define time dependent material properties, and as I mentioned, the notational size of the sections keep on varying, so you need to update them manually, but the program can do it automatically. So right click, go to properties, and there exists an option called change element dependent material property. So I'll click on that and then click on select all. Basically it will select the entire structure that is visible on your screen, and then click for notational size of the member, code is CEBFIP, and then click apply. The moment you do that, the program calculates all the notational size for each and every segment and then generates it into a table. So if I click on this button with 3 dots, I'll be able to see the notational size for all the sections. And when the program is computing the behavior under a different time or for creep and shrinkage, basically when it is computing the section properties, the program will automatically replace the value that we entered in the very first dialog box while defining the creep and shrinkage with the accurate calculated value. Again, a very time-saving tool. Having done this, now we'll apply some additional loads onto the structure. So I'll go to the elevation, right click, select loads, and under loads I'll select element beam load. Now here as point to be noted, in construction stage analysis, every load, boundary group, and structure has to be placed in boundary group, load group, or structure group. So I'll define a load case name first by clicking on this button with 3 dots and enter the name as SDL. And since this load will be applied during the construction stages, I'll now define its type as construction stage load. And then click add and then click close. Then similarly I'll define the load group. I'll click on the button with 3 dots, enter the name as SDL, click add and then click close. So now under the load group name I can scroll down and select SDL, and under the load case name also I'll select SDL. So basically this load case is being placed under this load group, and this load will be applied to the girders only. So I just use single select and select the entire girders. It will be a uniformly distributed load. I don't want to have any eccentricity assigned with it, so I'll just check off eccentricity and enter the value. Now the units are kips per inch, but the value that I have is in kips per foot. So what I'll do, instead of multiplying it by 12 times, I'll just change the units to foot and enter the value directly as minus 2.31 kips per foot, and then click apply. The moment I do that, you can see the loading being applied to the structure, and then I can click close here, and now I have applied the loading and assigned it into a group. Now I'll tell you where and when this loading will be applied. So I'll click on this button that is define construction stage, and let me first show you the construction sequence, how it is generated. So you can see the construction stage name, the duration. We have 3 tabs: element, boundary, and load. So at element tab it has 2 divisions, one is activation, one is deactivation. Activation means out of all the structure groups that you have, you can activate certain groups, and when you don't want them, you can put them under deactivated list. And until and unless you take out something or deactivate something, it is carried forward to the subsequent construction stages. And if you recall, the age of the peer that we entered was 100 days. So the program has automatically entered that. Group 10 and group 20 represents the peer table with the age of 15 days. Then come to boundary, you will see the supports and the elastic links and the loading, self weight, form traveler load, wet concrete weight, and the pre-stressing for the tendons in peer table. You can also create the load to be applied at a certain time interval after starting the construction stage. As you can see, the wet concrete weight is applied on the 7th day of this construction stage. That means 7 days in this construction stage was given to put up the formwork for the next concrete, for the next segment, and then the wet concrete day weight was applied on the 7th day onto this segment for remaining 5 days. And after this construction stage, if I go to CS2 and come to the element tab, you can see the new segments are activated with an age of 5 days. So all these things are automatically and carefully computed by the program and entered here. And since it is a iterative process, using a wizard is highly justified because it will cut short any human error that can creep in. And then automatically those wet concrete and form traveler 1 weight are put under the activation tab, and the new ones are added to the activation tab. So until unless you are very confident, and not confident, I mean very clear about using these features, you can, and frankly speaking, they are very simple. So if you just try your hands 1 or 2 times on these construction stage generations, you can create any kind of construction sequence within no time. And we have whole list of tutorials on our website that you can download and try them at your own time. So just cycling through the construction sequence, you can see that different loadings are activated and deactivated. This simulates the movement of form traveler onto the structure. Same thing with the elements. They are being activated. When the closed section is placed, we have different ages for them also. And under loads, we have the pre-stressing loads also coming into picture. And this is the final stage where I'll enter the duration as 10,000 days, because I want to see the permanent effect of creep and shrinkage onto the curve or onto the structure. And then I'll select the load group that I created, SDL, and just add it under activation tab, and then click OK. So in this way I can easily manipulate the construction stages, apply loads and modify them. And now I'll move on to the final step. I'll go to analysis, click on construction stage analysis control, and here specify the time dependent effect control. If you want to compute just creep or shrinkage or both, and auto time step generation for large construction stages, like for 10,000 days, the program will split the cycle or the duration into number of steps for internal computation. And then you can consider tendon tension loss effects for creep and shrinkage. You can see the tendon tension loss effect for elastic shortening. You can consider the variation in compressive strength. If you have entered rebar data, you can consider rebar confinement effect. And if you want the effect of time dependent behavior to be carried forward after construction stage analysis to the static model for live load and earth seismic analysis, you can just check this option, and that will also be taken care of. So but for the time being, we'll stick to this default options, and then we'll check on consider initial tangent displacement for erected structures. Basically this option will generate different type of deformation results. It will generate 3 results. One will be the camber diagram or the camber deflection. Second one will be the real deflection that will occur in the construction site, and the third one which is the deflection due to the existing loads onto the structure that is activated at that particular step. And then you can click on save output for current step, or the current stage for beam and trusses, and then click OK. Once you have specified all these inputs, you can just click on perform analysis, and I think it will ask me to save the file first, so let me save it with the name, let's say test1, and then I can you can read the progress that is there, that's being made in the message window below. It will show you what analysis is being performed, if any error message, or if the convergence criteria is not met during this construction stage analysis. Everything will be neatly listed down here. And when such an error occurs, then the program points out in which construction stage and for which node the error is occurring. And as you can see here, it just took 25 seconds to do this construction stage analysis, which goes to show the speed of the solver engine that we have in here. Now once the analysis is done, we'll start looking at the results. So let me go to the very first construction stage and start by looking at deformation results. So just right click, go to deformation and select displacement contour. You can see all the loadings that are applied to the structure are lumped together as dead loads, erection loads, primary tendon primary and secondary loads, creep primary and secondary, shrinkage primary and secondary, and summation. So for deformation, as suggested by the code itself, we should always consider all the primary effects along with the dead and the dead loads. So I'll click on summation, and you can choose to see the result at the first step, that is the first day of the construction stage, any user defined step that you have created in between, and the last step of that construction stage duration. This will include the time dependent effect also. So you just click on deformation and click on legend and then click apply. Now what you're looking at is an exaggerated deformed shape, but if you see the legend here and the units, you will be able to assess that it is exaggerated. So what you can do is you can scale down to make it more realistic, and as I mentioned, the program will give you different type of deformation results. So let me just cycle through few stages first. So this is the second stage, summation result. If I go to user defined step, you will see the deflection being reduced because the wet concrete is applied for this next segment, and then the last step, it will further decrease because of the applying of the moving of the form traveler to the next segment, and including the time dependent effects. So in same manner, we can carry on seeing the results at different time intervals. And right now you are looking at the camber values, but if I check on step stage real displacement and click apply, this is the real displacement deformation that will occur on the field. So you can see the deformation at different stages, or you can just see it in a continuous manner. So this is the deformation for you. Now if you want to see the deformation that is occurring just because of the loads that are activated in, let's say, construction stage 16 at the final step, click apply. This is the deformation occurring only because of the loading that is activated at that step. So sometimes engineers want to use this subtract different deformations for different construction stages to find out that due to which loading such enormous deformation is occurring between these two stages. So these kind of small manipulations are no longer needed in the software because they are very well integrated in the software. And if I check off construction current step displacement and just click apply, this is basically the camber value that should be considered while erecting the structure. But we have a very better, lot better representation of the camber diagrams. You can just go to result, go to FCM camber, and then specify the control, that is which structure group form your bridge girder, which structure group form your support nodes, and which structure group form your key segments, and then click OK. Then you go to result again, and under camber, FCM camber, you can click on FCM camber graph view. Now the camber graph can be created for different set of loadings. But right now by default we are choosing the summation to see the complete effect, and this is the camber diagram for you for the girder bridge. And if I just zoom in at a particular location, I just need to click and drag my mouse, and program will zoom in at that location. So you see there are two values at each node at different construction stage, and these two values represent, the top value represent the camber that must be considered while putting up the formwork, and the bottom value represents when the formwork is removed, what is the deformation that is occurring. So such detailed graphs are available in the program itself. You can then right click and zoom out all, but we have even better representation for this. So you can go to result, camber, and under FCM camber we have camber table. Again, you can choose for which loading you want to generate these graph or the tables. Upon hitting OK, you'll get the deformation at each and every node at each and every construction stage, and the cumulative effect as we go down. So you will see there are 4 pages. Page 1 is for the FSM portion. Page 1 and 4 represent the FSM portion on left and right end, and page 2, 3 are the intermediate segments. So if you have like more the segments, so you'll have more number of pages here. So page 2, it will show you the tree diagram right there. It will show you the cumulative deflections, and then if you look at closely into the screen at the final stage, if these deflections are properly met in this field, we'll get completely aligned geometry as zero deflection. So this was how we can view camber graph and table, and that this information can be directly handed over to the construction engineers, and that will save a lot of their time. And if you are dealing with precast segmental bridges, then the program has the capability to generate manufacturing camber also. So if these segments are erected, or sorry, are cast in factory and then brought to the site, the program has the capability to give you the prefabrication camber also. Now exploring more in results, we'll come to tendon time dependent loss graph, and I'll select, let's say, some tendon that was erected in the very beginning. Okay, so top O1 tendon, and I'll click on animate. Basically now you will see the construction stages and the steps are changing, and this graph is showing you the residual stresses in the tendons at different construction stage. So it's an animation. You can record this animation and use it later on. And then you can see there the final stage. This is the residual forces in the cables or the tendons. Then you can click close and then move on to result, and this information can be neatly laid down in tables. So if you go to result table and tendons, then you will find the option of tendon loss, where I can select one of the tendons and then select the construction stage for which I want to see the result. Let's say final construction stage, and then click apply. So here you will see the stresses after immediate losses, elastic deformation losses, the ratio, creep and shrinkage losses, and relaxation losses, all neatly laid down. And let me change the unit to KSI so that the numbers are more legible. And this information can be directly exported to Excel from here, or you can generate the graphs from here, or you can make it into a dynamic report table. Then other tendon results include tendon coordinates. So no matter how the tendons were generated in the program, you can obtain the coordinates for the tendons in the global coordinate system directly from here, and this information can be used for generating your tendon profiles or directly given to the field engineers. Then we have under tendons we also have tendon stress limit checks. Now this feature allows you to check the tendon stress at different locations. So you can select if you want to see the tendons for check for all. I'll click OK. Then you can specify at anchor how much is the how much should be the stresses away from the anchorage, and at serviceability or at service limit what should be the stresses as a multiplying factor of the given ultimate and the yield strength of the tendon material that we have defined. So once you specify these limits, you can just click OK, and the program will show you in red if any tendon is yielding at a given location. So this was all about tendons. And then during construction stages, you can also see element properties at each construction stage. So you can select the construction stage you are working in, and here you will see the starting age of that segment, the end age of the segment, and the elasticity at the start, and the elasticity, modulus of elasticity at the end of the end of that construction stage, and the cumulative shrinkage and the creep coefficient. So all these properties can be extracted after each and every construction stage, so that you can keep a check on them. And moving on, this was the element properties. Then similarly, we can see the bending moment diagrams throughout the construction stages. So you can just go to forces, you can go to beam diagrams, you can select construction, the load case and what step you want to look at, and then the program will show you the bending moment diagrams right there. You can turn on the legend and see their values. Let me change the units to Gibson foot so you can appreciate it more. In the same manner, I can cycle through different construction stages and you can see the results. Now if you want to monitor what was the bending moment during the construction stage in a particular member, you can just go to result, and then we have the option called step stage history graph, where you can select I want to have the result for beam forces, then click add new function, enter the name as moment, the element number, let's say I want to have focus on element 19 here, and at ith node then I want to monitor moment Y, and then it is a multi-case, let's say, and on the x-axis we'll have the stages, and then I'll select all the loads that are there and then click graph. So the program will list or draw the graph for each and every loading with different color, and throughout the construction stage you can see what is the bending moment value in that particular member. So this is one way of generating graph. Then same thing you can do with stresses. You can right click, go to stresses, you can see beam stresses, PSC, which is precast or pre-stressed concrete. So you can select the load case that you want. You can select 10 different points on the outer fiber location where you can generate results. So if you want to see the results at the top fiber location, you want to see the result for sigma xx summation, and you want to check on the legend, then click apply. The program will show you the stress values for due to dead loads on the top point. Then positions 3 will be the bottom fiber. You'll see this type of stress diagram, and again, so it can be generated in a graphical format. You can go to result and go to bridge girder diagrams, where you can select which construction stage, which step you want to create the graph for, and which load case you want to create the graph for, and what variable you want to have on the x-axis, and which girder group you want to focus on, and what component you want to look at in stresses. So choosing combine that includes the bending and axial stresses. And then you can have your allowable stress limits set here. Let me change it to KSI again. And then all you need to do is I want to see the result for current step, that is this one, and then click apply. So you can see this kind of curve given here for this loading. Then you can have for other load cases as well. You can have summation if you want, and then you can see the value for summations, and this is the bending moment for the summation, and these are the limits that you have defined, and the program has generated the limits for you. I mean, this is falling within the limits as of now. So this kind of elementary checks can be made before you move on to final precise concrete design, which we are going to cover in the tomorrow's session. So that was all I wanted to cover today, and if you have any questions, I can take a few right now. Otherwise you can write to me and give me the feedbacks about this seminar. You can find my contact details on your screens now. To all the existing users who joined in today, let me inform you that my contact details have been updated, so kindly update